Okay, hello. This is Daryl Worthy doing a recorded lecture for regression. So today we're going to do an example of mediation in R and show some of the different packages that have been developed to look at mediation and the different ways we can, uh, you know, run mediation analyses. So the way I'm going to do this, I'm not going to actually open up or like present the PowerPoint. I'm just going to have this kind of side by side with R over here. So here is R. Let me pull this down just a little. Okay, so this is what I've already, this is like at the end, I've already kind of run through this. So if you want to follow along, open up the mediation example.r script. So this is right here. You should have a copy in your Psych 671 RStats folder. So this script uses several new packages. Some of them were built specifically for mediation. So like the package mediation, that was built specifically for mediation. And so you probably have to install a lot of these. Remember, if you want to check and see if you have a package installed, you can look over here. So a lot of these I needed to install because this is a computer I've never run this script on before. So I would go through and install the packages on lines 5 through 10. So I recommend just doing them one by one. Just get on the line that you want to run, press Control Enter. So I'm not going to do it again because I've already installed them, but do them one by one, let them install, and then these load the libraries down here. So one by one after you're done, you can load the library. And so what you want is, down here there's no errors or anything, so that means that it effectively or successfully loaded the library. And so your installation was successful. If it says it can't find that library, then you didn't install it successfully. So you need to go back and try to install it. Hopefully everything will work. It worked on my end, and I have most of the packages installed that we've used in this course. But if you're installing it and it says it requires another package, then go ahead and install that package as well, and then try reinstalling the one that failed. So this is loading all of these. These are going to run like Sobel's test. We'll use this rock chalk package, just a way to plot simple slopes at the end. And then I don't know if we actually use the Stargazer package, but maybe we do. Okay, and so now we're going to make up a fake or synthetic data set where x, our x variable, so this is in lines 19 through 24, we're making up our data. And so x equals the motivation to succeed in graduate school. So it's measured at the beginning of graduate school, maybe some scale that instructors designed or professors designed, or maybe it's just some self-report. You report how motivated you are, so that's going to be X. And then M is the mediator, number of hours worked or spent studying on average per week. And then Y is the rating of the student's CV upon graduation. Now, I should say that I adapted this example from this link right here. So hopefully it still works. I made up this example basically about a year ago, so it's possible that web page is no longer online. But if you want to go see the original example, you can go to that web page. But I think I followed it pretty close, but I don't remember exactly. So go ahead and run these lines, line 19 through 23. So I'll just run these first, and then you can then we get our med data right here. And we could either view the header row if we wanted to, but if you want to view like all the data, you can in the console type view med data, and then it'll show you the data. So we created 100 data sets. Y is their like CV score at the end. M is number of hours per week they spent studying, and then X is the motivation variable that we created. Okay, so we have all of that data here. And so now we'll run the three models to use Barron and Kenny's approach. So on lines 28 and 29, I guess it's 29 and 30, run those to get the total effect C. So we can run this. We're regressing Y, dependent variable rating of the CV, on X, motivation to succeed in graduate school. So just as motivation to succeed, predict CV ratings at the end of graduate school. Yeah, it does. At least, you know, there's a relationship at the P is less than 0.05 level, so at least a modest relationship. So it appears that the total effect is significant. That's what we get for C. Now, next we'll run our A path and our B path. So first in lines 33 and 34, run that to get our A value. So we run that. You just get on a line and press Control Enter, and it'll run it. And you can see that it's highly significant. So I pasted this output over here. So there's a significant relationship between X, motivation to succeed in graduate school, and predicting hours worked per week. Then run lines 37 and 38 to get the B and C prime effects. Oh, I'm in PowerPoint, so it doesn't like Control plus Enter. Okay, so this is the multiple regression of Y regressed on X and the mediator. Okay, we can see that the mediator is significant. So controlling for X, motivation, hours worked per week, predicted ratings for the CV. And then C prime, the direct effect after controlling for the indirect effect with the mediator, it's not significant. Okay, so we have from Barron and Kenny's approach, C, the total effect from model 1, that was significant. A was significant, the mediator regressed on X, and then B was also significant. So the dependent variable Y regressed on the mediator controlling for X. So we have total mediation as well because C prime right here is not significant. Okay, so that would be like how we do, you know, a mediation from Barron and Kenny's approach. Just run these three regressions. So we appear to have significant mediation from Barron and Kenny's approach. We'd also have significant mediation from the joint significance. I think I should probably put approach, not effect. So we have both, because joint significance only requires that A and B be significant, and both of those were. To get the actual A-B effects, we can just multiply. We're just taking the coefficients from fit A. So this is going to be in line 41. The second coefficient from fit A, that's like the non-intercept coefficient. And then also from fit B. Okay, so that's also the second coefficient listed after the intercept. And so we can multiply those together and get our A-B effect. So A times B, those coefficients come out to 0.24. Okay, and so that's like our, you know, numerical indirect effect. So we can run a Sobel test to directly test whether this indirect mediated effect, A times B, is different from 0. So whether it's like significant, basically. So you can run line 46, this question mark Sobel. It will tell you how the Sobel function works. So this question mark function is very useful, of course, for, you know, any function that you want to learn more about. It's from the multi-level package. Estimates Sobel's indirect test for mediation. The function provides an estimate of the magnitude of the indirect effect, Sobel's first-order estimate of the standard error associated with the indirect effect. So it gives us Sobel standard error and the corresponding z-value, which then we could do, an inferential test. At p is less than 0.05, we're looking at whether the absolute value of z is greater than 1.96. Okay, so it's just going to basically run kind of Sobel's data for us. So all we have to put in are the predictor, our predictor variable, the mediator variable, and the outcome variable. And so that's what I've done here. I reference med data, and then this money sign tells it to get an individual column or variable from that data set. So we have X, our predictor, M, our mediator, and then Y, our outcome variable. And we can go ahead and run that. Okay, so run line 47. Let's see, skipping ahead. Run line 47 to run the Sobel test. So here's our results right here. It'll show the same output from the 3 models that we ran, then the indirect effect. So it runs these models, that we ran at first. So this was y on x, y on x plus m. So this is actually what we called model 3. So you just have to, be aware that it's just doing it in a little different order. And then y of our m regressed on x. Okay, so it runs those 3, and then it gives us our indirect value, the standard error for the indirect value, and then of course the z value right there. And so that's the stuff. So z is greater, the absolute value is much greater than 1.96. It's 3.887. And so obviously it's significant. But we could, if we wanted like an exact p-value, we'll be able to get those down here. So we could also use the mediation.test function from the BDA package to give us an exact p-value. So that's this mediation.test function right here in line 50. So run line 50. So I'll just be on line 50 and press Control Enter. Okay, and this gives us our exact p-value, and also gives us, the Sobel value. I'm not quite sure what these other values are, probably just slightly different ways of computing the mediation test, but if you want, you can look up Aurorian and Goodman. So they probably came up, with some slightly different way to kind of compute the indirect or mediated effects. But it gives us an exact p-value, so p equals 0.0001. So very significant from the Sobel's from Sobel's test. Okay, so bootstrapping, a lot of people claim that that's a better option than just using Sobel's test, because we could come up with those like weird distributions for the AB indirect effect. So Sobel's test, criticism, we talked about those in the earlier lecture, just covering the concepts of mediation, but it's considered a little bit dated and inappropriate since it assumes that the AB effect is normally distributed, and that's not always the case. So run line 53 to give some information on the mediate function. Okay, so we type in question mediate and then run that line. So it's used to estimate various quantities for causal mediation analysis, including average causal mediation effects. I think that's going to be abbreviated ACME. So not like the brick or whatnot, but that's the indirect effect, the average causal mediation effects, a long-winded way of saying the mediated effect or the indirect effect. The average direct effect, so that's like C prime, so you can look at that as well. Proportion mediated, we talked a little bit about proportion mediated, and then the total effect, just overall, what is C, the regression of Y on X. Okay, so we got some information. Now we know kind of what we're looking for with this package. And of course, it also tells, all of the different inputs that you can put into the model. So we'll see some of those inputs that we put in. Okay, so run lines 55 through 58. So this is this right here. So we basically run these models first to get M and Y. Okay, and then we use those in this fit med function. So we declare the treatment to be X and then the mediator to be Y, because those are the actual labels from our data. We labeled them X and Y. If you labeled them, something different, you would want to put in whatever the names of your variables are here. Okay, and so we can see the results are right here. ACME, the average causal mediation effect, is the indirect effect. Okay, so we can see it's the same thing that we got earlier, 0.2417. A lot of this is just kind of different ways of testing for mediation using different packages. So the estimate is the same as what we computed earlier. ADE is the average direct effect, so that's C prime. And then the total, so the direct effect is actually negative. If we go up just a little bit, we can see that the actual effect is negative right here. So negative 0.09. So it's actually an example of suppression where this becomes like a negative effect. And it was positive before just in the, so this is just with the predictor in itself, it's positive, weakly positive, but here it gets suppressed to where it's the opposite direction. So, and then proportion mediated is the ratio of the direct effect, so 0.2417 to the total effect, 0.1448. And because the direct effect is negative, we actually have like a smaller total effect than the indirect effect, and so we have a proportion mediated that is not between 0 and 1. So that's one of the criticisms of like this proportion mediated statistic, is that it can be outside of the bounds of 0 and 1, so it can be greater than 1. Okay, you can run line 61 to plot this fit med. So this is like what the outcome of the mediate function gave us. And so this just plots these different effects with their confidence intervals. And so you can see I have the indirect effect up here. The direct effect's not different from 0, so its confidence interval overlaps with 0. But then the total effect, its confidence interval is outside of 0, so it doesn't include 0. Okay, so the indirect effect is significant, total effect is significant, but the direct effect is not significant. So now let's actually run a bootstrap. So run lines 64 through 65. So fitmed boot, this is using this mediate function again, but now we're telling it to, you can declare boot equals true. So that means that it's going to do a bootstrap, and we tell it how many simulations to do. 999, that's just kind of arbitrary. We could pick a different number if we want. We just want it to be sufficiently large. And so bootstrapping, again, we'll do a manual bootstrap below, but basically what it does is it samples with replacement. So it gets from our data set of 100, it samples 100 data points, but with replacement. So the data will be slightly different each time, basically. And then it computes that AB indirect effect for each sample, each of the 999 samples in our simulations. And then it basically comes up with a distribution of those AB effects. And we can get like the confidence interval, the central value of that distribution. And so we have our AB effect, but it's been bootstrapped basically to allow for like a different shape of the distribution than a normal distribution. Okay, so run lines 64 through 65. This will get us our bootstrapped results. So it's running, it's going to take a minute running non-parametric bootstrap. It's thinking. Okay, that means it's done. Okay, and so we get a summary of fit med boot. So similar to what we have up here, the the indirect effects, average causal mediated effects, about the same thing. Okay, and then the average direct effect right here, the total effect right here. Okay, and then the proportion mediated right here. So everything is pretty similar to when we just did no bootstrapping. So in this case, with such huge effects, we're probably not going to have like issues with not doing bootstrapping because the results are going to come out about the same. Where we might get like kind of weird distributions for AB is when the effects are a little bit smaller and closer to zero. That's when we're probably more likely to get a distribution that's non-normal. So now let's run our own bootstrap to see if we get the same result. So we can also use ggplot and geom histogram to plot the distribution of the AB effect. So run lines 72 through 76. Actually, make sure you have run line 71. That loads tidyverse, which you probably have installed because we've been using that a lot in this class throughout the semester. But if you don't have that installed, then you need to type install packages and load tidyverse or install tidyverse. Okay, so we run line 72. Tells how many simulations we're going to run. We're going to do 1,000. Sample size is 100. So we would want to use the same sample size from our sample. And then we have other things right here. Okay, we're creating a vector right here for the direct effect. Actually, that should be indirect effect, but we're going to call it the direct effect, I guess. So we have a vector here. This is going to be like the AB vector that we're going to compute for each of our 1,000 simulations, and we're going to like store them there. So we're creating a vector that basically is all zeros for a number of sims. So 1,000 zeros basically. Okay, if I want to see that, I can actually type direct effect. Okay, and it's just a bunch of zeros. When we go through, it's going to fill this vector and replace these zeros with the direct effect values. Okay, so let's see. So now we're going to actually run the bootstrap. Run lines 79 through 85, and I'll explain a little about what each line does. So it'll take a minute. It didn't really take that long. So it ran all 1,000 of those in a second. So this is a manual bootstrap that I basically did using a few different functions and a for loop. So it runs a for loop from I, just the iteration, that's like just a dummy variable, in 1 through number of sims, so 1 through 1,000. So I'll take on a value starting with 1, it'll go all the way to 1,000. And then for each one of those, we're going to sample some current data. So we use this sample n function, and we sample with replacement equals true. We sample from the med data, and then our sample size is 100. And then replace equals true. If you want to learn more about the sample n function, you can type question mark in your console and then sample underscore n. Okay, and then line 82, we take our current data and we get the m to x regression, m on x regression. And then in this line 82, we basically get our b. So we regress y on m plus x. Okay, and so we're looking for this m coefficient. Okay, and then basically to get the direct effect, we take the second coefficient from this model, so from fit AM. Okay, and then we take also the second coefficient, which will be the m coefficient, so the effect of m on y controlling for x. So we get that, so that's b. So this is a right here and b right here for each one. And then that's going to be the direct effect for iteration I. So then this vector right here, like if I equals 1, well, then that'll be the value. This will be the value for I equals 1 right here. For the second simulation, I equals 2. The second value in this direct effects vector will be this right here, and so forth. So, oh, I'm not in R. So if I go ahead and run this, okay, so I ran that. Now, if you want to see how we've populated this direct effect with direct effects, you can just type it in. Okay, I think below I actually get a header for it. So you can see these are all of our A/B effects for every bootstrap sample. So recall that the one we computed was 0.24, and so you can see that these are all, around 0.24. Some are a little less, some are a little more than 0.24. Okay, so that's why we do bootstrapping. We get kind of this distribution that central tendency will tend to cluster around like the value we actually computed directly from the data. Okay, so now we have a vector of 1,000 direct effects running lines 88 and 89. Says to make this direct effect as a data frame. So that's something you do a lot just to get, I think basically it helps when you're using like tidyverse and ggplot to have everything in a data frame where the columns are named something specific, and that's kind of the best format to go into ggplot. Okay, so run lines 88 through 91. Okay, and there we get our header. So this is just the first 6 rows. Up here we looked at all 1,000, but you can see that the first 6 rows should be right there. Okay, and we labeled the column names for this direct effect. Now it's a data frame, so it's just there's only one column, so we just labeled it AB. Okay, so now let's plot the distribution of AB using tidyverse and ggplot's geom histogram. So we just take the data from direct effect. Our aesthetic is just x equals AB because that's the variable from our direct effect. Okay, and so we run that, and there's our histogram. Now, of course, this is a bootstrap sample, so it's going to look slightly different each time you run it. Okay, because it's bootstrapping, different values and simulating different data sets. So, when you bootstrap, it'll never come out like exactly the same way, basically. Okay, so your histogram will look different because they're simulated and they're not the exact same every time. Okay, we can use the Quantile function, which I think is just a base R function, to get the 2.5 and 97.5 percentiles by running line 99. So this will give us like a 95% confidence interval. I think last year I actually made an error and I got like a 90th percent confidence interval because I got the 5th and 95th percentile. So that cut off 5% of the distribution at either end. But we only want to cut off 2.5% of the distribution at either end if we're getting a 95% confidence interval. If we were getting a 99% confidence interval, we would only want to cut off 0.5%, the top half percent at each end. Okay, but we can use Quantile, and it'll tell us basically what are the values for the lower bound of the 95% confidence interval for AB, and then the upper bound for AB. Okay, and then the estimate of the effect is the mean value. So just run line 102 to get the mean of all of these AB values. And so this will be like what our bootstrapped estimate is for AB. Okay, so it's also 0.24. So you can see it'll be slightly different. Last time I ran it, it was 0.2403. Here it's 0.2415. So just slightly different values. I think you can even get values of like 2.3, or they can kind of vary a little bit. So run lines 105 and 108 to get the median, so the median rather than the mean of the distribution. You could choose to have that as your central point, if you wanted to, but you can get it in two different ways. So on line 105, we get it by just getting the exact 50th percentile point. Okay, and so the median in this case was 0.2358. So it's a little bit of a right skewed distribution. The median is a little bit to the left of the mean. The mean is kind of pulled toward the skew. Okay, and then we can also get the mediation by using this median command. So that's just like the mean command. So these will produce the same thing basically. So the median, of course, is again a little less than the mean. So just as a quick example of moderation, we've already covered moderation, with interactions. But here's another quick example. The main new thing I want to show is this plot slopes function from the RockChalk package. I guess I should, well, maybe I'll just type it wrong so it fits in one line. Okay, so run lines 112 through 120. This is actually going to like create a new data set basically, and I'll go through what this data set is. This is like just another example that I took. Let's see, so yeah. Okay, so here's our example. So X right here that we created, it's going to be a sample size of 100. X is our independent variable, the number of hours slept by the participants, say slept the night before. Z right here is going to be the moderator. We added in just some systematic variance for our dependent variable that we're going to compute down here. So Z is our moderator. This is ounces of coffee consumed. So hours of sleep might be related to the ounces of coffee consumed, which then in turn might be related to the dependent variable, a measure of attention paid during class. Okay, and so this is our dependent variable right here. So now run lines 123 through 129. This will 123 and 124 create centered variables for X and Z. So Z is our moderator. I'm just calling it Z to not get confused with the mediation example above. Okay, so here are results right there. So this is just the actual data. Okay, and then line 128 runs our model. So run lines 127 through 129, and then we'll get our actual model here. It looks like the interaction term is significant. So we ran a model with an interaction. Okay, so it looks like there's an interaction. Now run lines 133 and 134. This uses this RockChalk package and this plot slopes command, and it actually plots like the slopes for you. So we just had to put in the plot for X is XC, the moderator is called ZC. So X is like what we've talked about as our proximal variable, and the moderator is our contextual variable. Okay, and so we can see that the effect of sleep on attention paid is moderated by caffeine consumption. So at low levels of caffeine consumption, there's kind of this weak relationship between sleep and attention paid. Sleep is centered. Of course, as sleep goes up overall, more attention is paid. But then at like high levels, so this dashed line for the moderator, coffee consumption right here, at higher levels of coffee consumption, there's like a steeper relationship between sleep and attention paid. So of course this is just kind of a made-up example. We won't get too much into it, but this plot slopes function from the RockChalk package could be useful if you just want to quickly plot your simple slopes. Then of course you could, if you're going to use them for a publication, you might want to plot them like we did with ggplot or something like that to make like a better, more professional looking plot. Okay, and then finally, if you've installed the BRMS package, you can run lines 137 through 140. So I'll go ahead and start it because it's going to take just a minute to run it. So we ran our BRMS package, or loaded the library right there, and then we run basically the same data. We run it on the uncentered data in this case. We could choose to put in the centered variables as well if we wanted to. Okay, and I think note that this notation is a little bit redundant because all I really need here is x times z and xc times zc right here. Okay, but it just took a minute for it to run, and so it finished. With BRMS, we're interested in whether the credible interval, so this is the lower bound for the 95% credible interval, and the upper bound, we're interested in whether that interval includes 0. So the lower bound is 0.15, the upper bound is 0.32. That's well away from 0, so it suggests like a strong effect. Now, this conditional effects command is what I think is really useful, like the plot slopes. First, it plots like the lower order effects, the effect of x on y, and then the effect of z on y. But what we're really interested in is this like final plot. Okay, and so we can see at low coffee consumption, a shallower relationship between sleep and attention paid. But then with higher amounts of coffee consumption, there's a stronger relationship. Okay. So that's basically it. And if you've watched the earlier lectures I gave, we could then take this plot right here and we could edit it and make it put better axis labels and a title if we wanted to and things like that. Okay, so that is pretty much it for this mediation lecture. And so in the next one, I'll talk about logistic regression, an example of that in R. So hopefully that's been helpful, and I definitely encourage you to run through the script and verify that you can produce all of these plots and things like that yourself. And hopefully it'll be useful in your own analyses. All right, so that's it for this one. Thanks.